Okay, guys, lesson 29. Well, we get to start off with a little bit of calc history.
Oh boy. Story of one.
No, calc history.
That was exactly.
Not the history of
That's
one,
my favorite video.
calc history. Okay, so, Sir Isaac Newton, which you guys have already been joking about, and Leibniz. I don't know, Gottfried Wilhelm Leibniz. Anyways, okay, so an Englishman and a German, they were both credited for inventing calculus separate of each other. Okay, so this takes us back to 17th century, and, so basically you had a lot of the same thoughts, but they were different places. It's not like they were emailing back and forth back then, so, or even calling each other back and forth, totally different. So, in terms of derivative, okay, so to designate the derivative, Newton used y dot. And so y dot meaning that there would be a dot over the y. Okay, that was his notation for derivative. Was y dot, a dot over the y. Okay, over the years, it's been changed to what we say prime. And so when we write something, we write y prime like that. Okay, so I don't know why it was changed or, but that's just what's happened over the years. Leibniz, okay, he used the form of the derivative, the dy over dx, which we also use today, right? So when we talk about dy dx, I've kind of just thrown it in at you. We haven't done a whole lot of explanation, but we're going to do a little bit of that today. But the fact that dy over dx is a fraction, yes? And so even though you haven't seen them separate up until this point, you can separate the dy and the dx. And that's what takes us into what is called differentials today. So notice he said to get rid of the dx, he simply multiplied it to the other side to leave dy. And that's the notation we're going to use today, is talking about differentials. Okay? So when we have done okay, I'll explain, I guess, into more detail after we look at our first example. So, definition of a differential. Let y equals f of x be a function that can be differentiated. So when we talk about something that can be differentiated, that means something that you can take the derivative of. Okay, so if I talk about is this function differentiable? Can we differentiate? That means can you take the derivative? And eventually you will learn some functions or some specific points on functions where you cannot take the derivative. That's to be come at a later time though. The differential of x, denoted as dx, is any non-zero real number. The differential of y, denoted as dy, is given by dy equals f prime of x dx. Okay? It's all about notation. What I've had you writing in the past, when I say take the derivative, when we take the derivative of y, I just have you writing either y prime or dy dx. Then when we take the derivative of the x's, we just take the derivative of the x's. We don't put anything with them. Differentials work a little bit differently. So I'm going to show you kind of two different ways to do this and how it all relates. Let me use, okay, side note before I go there though. If you have the equation, y equals f of x, and we say take the derivative. Okay, so before this is kind of pre-example one. What do we often write when we take the derivative of a y equation? In place of y, we put what? dy dx or y prime, right? I think I heard both out there. So I'm going to use dy dx. Okay? When we take the derivative of f of x, if, equation starts f of x, how do I write that as a derivative? We usually use our prime notation, which means the derivative of f of x written with prime would be f prime of x, yes? Now, think about it. How do I get rid of a denominator, such as dx? You multiply by dx, right? So if I multiply this by dx. That means if you multiply by dx on the left, multiply by dx on the right. And so now, dx's cancel. I have dy equals f prime of x dx. And I'm just trying to show you where they get this dy equals f prime of x dx. Again, what you're used to doing is saying, okay, I'm going to take the derivative of y with respect to x. And then over here we just take the derivative. So derivative of f of x is f prime of x. What this is saying, and you could go, with differentials, you could go straight from y equals f of x to this dy equals f prime of x dx with the idea that, okay, what is the derivative, if we were thinking in terms of x, what is the derivative of just a y? What would be the derivative of one y? Well, no, in terms of, okay, so let me ask this. What would be the derivative of x? Just the variable x. 1. Are we there? I'm not all convinced you guys are all there. I've got some looks say what. So if I'm asking the derivative of x to the first, then 1x to the 1 minus 1, which just 1x to 0, which is 1, yes? Could we do the same thing with y to the first? What would be the derivative of y to the first? A 1, yes? Okay, you could do that with any variable, yes? What would be the derivative of a? 1. Okay, you see where I'm going with that now? Sorry, I wasn't making a good connection. So the idea here is the derivative of y is 1. What variable did I just take the derivative of? It was a y variable, so we tack on a dy. Okay? Derivative of f of x is f prime of x. What variable did I just take the derivative of? An x variable. So you can tack on a dx. And so this is a different way to do derivatives. Okay? Now, let me go for a specific example, and I'll tie it in even a little bit better. Okay, so let's go over here to example 1. Let's go with what you know. They're asking us to find dy. We'll get to that in the end. Normally, what do you do? When you're asked to take the derivative, in place of y, what do we normally write? I'm looking for the dy dx one. Yes. Okay? Now, since we've already written dy dx, derivative of y with respect to x, because there's x's in the equation, just take the derivative of each term. So derivative of 3x to the negative second. Negative 6x to the negative third. Derivative of 2x squared. 4x. Derivative of 1. 0, nothing. Okay. We're being asked to solve for find dy. How do you get dy by itself? Multiply by dx. If you multiply the left by dx, we're multiplying the right by dx. Now, there's two different ways we can think of this. dx's cancel on the left, so you're left with dy. One option is you can leave this with parentheses. Negative 6x, negative cubed, plus 4x, quantity, times dx. Or we also have the option of taking that dx and what? Distribute it. So I want to write that out. dy is equal to negative 6x, the negative third, dx, plus 4x, dx. Now, I'm not sure how great I'm going to do it, how great I'm doing it connecting this, but the first line is what you're used to doing, yes? Just when you see the y, it's a derivative of y with respect to x, and then with the x's, you just take the derivative, because we've already put in the dx on the other side, and that's fine. But when they talk about using differentials, That's why when you take the derivative of each term, with that you put a differential, d, and then whatever variable you just took the derivative of. So the derivative of y is 1, and so it's 1 dy. Derivative of 3x and negative 2, negative 6x and negative third times, which variable was it? Dx. Derivative of 2x squared. 4x times which variable was it? Dx. Okay, and then we don't have to worry about the 1. Okay, are you seeing a little bit of how that works? Because it's one of those things you kind of have to know a little bit of both ways. There are times where we want to use differentials. There are times where we'd just rather say dy dx. Kind of depends on what we're doing. One more example. Y equals sine x plus cosine x, find dy. Officially, you could go straight to it if you want. In that, what's the derivative? If we use differentials and we go straight there, what's the derivative of y? Okay, not the direction it's going, but I can go there. Okay, so derivative of y, if we're just doing our normal derivatives and not thinking differentials, derivative of y, dy dx. Derivative of sine x is cosine x. Derivative of cosine x. So negative sine x, I'm going to write minus sine x. How do I write this with differentials so that the dy dx is separated? Multiply by dx. So then it's dy equals, now I'm going to do quantity of cosine x minus sine x times dx. And that dx can be distributed. So dy equals cosine x dx minus sine x dx.
We're talking about like taking the derivative, like meaning like 1.
Right. Well, so what I was trying to have you guys do, and
As soon as you showed like that's not the direction you're going, I was like, oh,
that's all right. The point I was trying to make is, could you possibly have just gone straight to that final answer without doing the middle steps? Yes. In that the derivative of y is 1, and then which variable? Dy. So times what differential? Derivative of sine x is cosine x times what differential? The dx. Derivative of cosine minus sine times what differential? Dx. Okay? And obviously this is only going to work if you have two variables in a problem. It can't work with more than two variables or anything like that. Okay. Questions?
That was easy.
That was all the homework was.
I think we can play a lot.